join us today for our MedPL. Actually, should we record?
I am recording. I'm assuming Santosh signed the form. Is that correct?
Yeah.
Okay, cool.
So, well, then thank you, Santosh, for joining us today. And so Santosh, he was, I guess, a classmate of mine when I joined the University of Pennsylvania as a PhD student. He was already there for a couple of years when I joined and did this PhD with Milo Martin. I guess even though it wasn't, and Amir, Ramami. And so he has some ties to Wisconsin, I guess, since Milo was a student here. And so Santosh is now at Rutgers, and he has been doing a lot of interesting work in compilers. And today he's going to tell us about Posits.
Okay, let me get started. And thanks, Oz and Loris and everyone else who's attending this talk. So today I'm going to talk about like some of the foundational things in computer science, right? How do you represent numbers and how do you reason about them? And this is typically part of CS curriculum. Like I teach 211, like I teach, which is a computer organization, I teach number representations. And people don't wake up one day and start thinking about number representations, right? Let me tell you my story of how I started working on number representations. My group, since I've been at Rutgers, has been focusing on lightweight formal methods for LLVM verification. As part of it, we have been formalizing the semantics of the LLVM compiler at various parts of the LLVM compiler and building automatic verification tools for people optimizations. And as part of it, we realized like most of the bugs in the LLVM compiler primarily comes from undefined behavior. And we initially focused on the integer subset of the LLVM IR. And then I had a fantastic student, David Menendez, who has since graduated. And he said the LLVM, he observed that the LLVM's floating point instruction set is even more ill-specified than integer instruction set. So initially, as a start, we built a bit-precise verifier, people verifier for floating point optimizations, which we called alive FP. And then there is this interesting mode in almost all mainstream compilers called fastmath. So effectively, what does fastmath do? It treats every real number identity as a floating point identity and optimizes the program. So associativity is not true with floating point, right? But the compilers treat it, and it's very important for vectorization, and it's deployed. And what we observed was like you run an application with compile it with fastmath and observe the execution, it produces really counterintuitive behavior. And we wanted a debugger to debug why is this fastmath producing all this counterintuitive behavior. And that's how my foray into floating point started, and floating point and its variants started. And at the same time, I observed like floating point performance is amazingly important in many domains. And people are proposing a lot of new representations. One such representation that's getting a lot of interest is Posit, which provides tapered precision. And Google recently proposed like bfloat16. It's available as part of its ASICs and Intel FPGAs. So, and NVIDIA just 2 weeks ago proposed TensorFloat32, which is a 19-bit floating point representation. And the key driver for all this is floating point performance for machine learning and HPC domains. Okay, so there's a lot of interest in using new representations and performance, but there are not enough tools to debug and detect numerical errors. Like this is one of my pet peeves, right? So computer scientists used to think a lot about numerical errors in the 60s, 70s, 80s, but modern CS majors can't even identify numerical errors in their own code. Like I've seen code people write like compare two floating point numbers with equality. And more strange thing that we observed was even math libraries that we take for granted, like you call sign of X, right? They produce wrong results. And today's talk is going to be, I'm going to give you a tutorial on a new representation called Posits. And how do we build a debugger, which detects a lot of numerical errors with long-running applications with any representation of your interest. But I'll primarily focus this talk on Posits. And as part of this exercise, when we built this debugger, we ran it with a lot of interesting applications. Then we observed that math libraries itself produce wrong results. So I will tell you how to design correctly rounded math libraries. How do you design correct math libraries using a new technique that we are really excited about. Okay, so let me get started. So let me start by giving you a tutorial on Posit. What is a Posit? Posit is a new representation proposed by John Gustafson, who is now one of my collaborators. John has fancy titles for all his books. He calls posits the end of error, but I don't believe posit is the end of error, but it's definitely an interesting representation. Why is posits exciting? It can provide more precision than floating point given the same number of bits. And with tapered accuracy, I'm going to illustrate it as I go forward. And with the same number of bits, it can provide better dynamic range for certain domains. So now I'm going to tell you how posits provide better precision or tapered precision compared to floating point, right? In this figure on the slide, what I'm showing you, the x-axis is the range of numbers. You have a 32-bit floating point number, all the numbers that you can represent with 32-bit floating point. So the floating point is classified into 3 categories, right? Normal values, denormal values, and special values. The general expectation is like you don't use denormal and special values. So the y-axis is the number of precision bits that you have. So for the normal values, floating point provides 23 bits of 23 fraction bits or 24 bits of precision, right? So this is why you have a flat line. And then floating point has a gradual underflow. So very small numbers don't immediately drop to 0, but like they'll gradually underflow to 0. So that's why you see the slope at the left-hand side of the figure. So how is posit different? Posit provides precision as shown in the curve on the slide. So for numbers between 1 million and 1 by 1 million, posits provides more precision than floating point with the exact same number of bits. Okay, and then as you go to higher ranges of numbers, the precision actually drops. So this is Posit has this idea of tapered precision everywhere, which is kind of interesting. So now if you can scale all your results to fit in this range, 1 million to 1 by 1 million, you are getting better precision than floating point. So this is the promise of posits. So again, posit like tapered precision is not it's not something really new, right? Like there is Morris float, which was proposed in 1971 by Robert Morris, which attempted tapered precision. But the cool thing about posit is it's a practical, usable implementation of tapered precision in two's complement, which you can reason with two's complement arithmetic, which is kind of interesting. Okay. So this is what tapered precision was. Like what is another exciting thing? Why are people excited about posits? You can approximate a sigmoid function, which is widely used in machine learning in a given posit configuration by bit shift operations. You flip the first bit, right shift by 2 bits, that approximates a sigmoid function. So you don't have to call complicated math libraries to do that. So this has created a lot of interest in especially in the machine learning community to use posits. And there's a cool paper from Facebook recently, and how there's a log numbered system which was inspired from posits actually does very well with deep learning. And there is a recent paper from NVIDIA anonymous group from Caltech, which states that quantization works amazingly well with tapered log number system. So the summary is like if you don't know anything about posits, go do look at it. There is like amazing opportunities to do really cool work in this space. So hopefully I've given you a lot of I've created a lot of interest about posits with this brief introduction. So let me go into the details like now. So this is a background on posits, right? Like let me tell you how posit actually represents. So typically a posit number is characterized by 2 parameters. One is n, which is the total number of bits, and es, which is the maximum number of bits you're going to use for the exponent. Okay, so a posit configuration is n, es. N is the total number of bits, es is the maximum number of bits for the exponent. And the first bit is a sign bit. If it's a 0, it's a positive number. If it's a 1, it's a negative number. So the next sequence of bits are called as the regime bits. So you have a consecutive sequence of zeros followed by a 1, or a consecutive sequence of 1s followed by a 0. So it could be the entire bit string, or it will stop. Like so, it's a run length encoding of zeros and 1s. Okay. So these are called as the regime bits. So regime bits contribute a very large exponent to the eventual value of the number. So there is a super exponent that is defined for a POSIT configuration. What is the super exponent? It's 2 raised to the power of es. Where es is the number of exponent bits that you're going to use for the configuration. So this is a super exponent, which is also called as the U seed in the POSIT representation. And depending on the number of regime bits that you have, the contribution of the regime to the value of the number is U seed to the power of k. And what is k here? If your regime starts with a 0, it has a consecutive sequence of zeros followed by a 1, you count the number of zeros and minus k, minus the number of zeros. Minus 1 times the number of zeros is your contribution to the value of the number. You're representing a very small number. So in contrast, you have a sequence of ones, a consecutive sequence of ones followed by a 0. You count the number of ones, and the number of ones minus 1 is the contribution to the a value of the number. You take the super exponent, raise it to the power of k. That is the contribution to the value of the number. So it will become clear, like again, like I'll demonstrate it with an example. So after the regime,
about the super exponent.
Yes.
This is Mark.
Yeah.
So with an exponent, when you're doing multiplication, you just add exponents. But with a super exponent, it seems way more complicated. So are you going to show us later how there's a reasonable implementation for this and hardware?
So I'm not going to talk about how the hardware implementation of super exponents, but John has a couple of RTL designs how to actually do this. John Gustafsson, who's the proponent who proposed Posits, has RTL designs where it shows like you can design a floating point data path with almost the same latency as a regular floating point. Yeah, you are exactly right. You have to, since the bit patterns are not fixed, right? You have to have a run length encoding decoder to identify what is the contribution of the regime to the value of the number. So his design uses count leading zeros circuit to actually identify the number of regime bits. So it can add to a bit to the critical path, and he shows in his design it's like 1 cycle of additional delay, not much. Okay, so after the regime,
this is Tom. I have another question. It looked like the regime bits it's doing some kind of unary encoding.
Yeah,
so it's weird when bits are expensive. Why couldn't that have been done in binary? Or is it the fact that you have to be able to know where the end of it is by the complemented bit?
So again, this is one encoding. So there are 2 things I think John Gustafsson was trying to accomplish. Create, like, you want to compute the negative of the number just using 2's complement arithmetic. Just take the negation of it and it should be a complement of the number. He had to work out the entire math. So with this encoding, you can create the negative of the number just by taking the 2's complement. So there are like various trade-offs that he had to address, and this is the design that he came up with. Okay, so then if there are any bits left after the regime, you can have up to es number of bits of the exponent, and then the remaining bits are fractions. Okay, so let me actually illustrate with an example like how the bit pattern actually looks. So this is what NES configurations. You have a sign bit, regime guard bit, and sum of exponent bits and fraction bits. So the regime guard and the exponent together encode the exponent of the final number. The regime and the exponent together encode the final exponent of the value that you are representing, and the fraction bits encode the fraction that you are representing. So let's look at a 32-2 configuration, which is which is intended to be a replacement for a 32-bit float. Let's say you have a bit pattern like this. The first thing you notice is sign bit is 0, it's a positive number, and then you have a consecutive sequence of zeros. So this is the regime, and you have lots of reasonably high number of zeros. So you raise the super exponent, which is 2 to the power of 4 here, 2 to the power of 2 to the power of 2, which is 2 to the power of 4. So you raise 2 to the power of 4 to the power of minus 14, because there are 14 consecutive 0 bits. And then you have a regime guard bit. Then you have ES number of exponent bits. In this case, it's just 1, and the rest is the fraction bits. Okay. So if you use the key thing is here, let's look at another bit pattern. So in this case, you just have one bit for the regime, which your regime is 1, and then you have a regime guard bit, and you can repurpose the rest of the bits to represent the fraction. So if you use small number of regime bits, your final exponent in the number is going to be small. So you can repurpose, like, your more precision to represent the number. And if you use more number of regime bits, so like, let's look at this number where you have a lot of ones, it's representing a very large value. So the exponent of the resultant number is going to be very large, and you have very few fraction bits. Okay. Essentially, by using the regime, it's able to provide tapered precision with a given number of bits. So this is what the excitement is. If you can somehow scale all your values to lie within a small range, and then you have more precision than floating. Okay, so
do you get rid of denormalized numbers and the special numbers like nans and infinities?
Yes, so there are no denormal values. So one way to think of Posit is it's a tapered accuracy everywhere. Like floating point does have tapered accuracy. It's only for denormal values, right? Posit goes to the extreme where like it's the tapered accuracy everywhere. So there are two special values. There are no nans. There is a 0. There's a special bit pattern, which is all zeros is 0. And then there is a 1 followed by all zeros, which is a special bit point, which is not a real, which is used to represent not a real, NAR.
Okay.
So which is used to represent exceptions. And another interesting thing that Posit did, there is no overflow and underflow. So if you reach a number which is larger than the maximum representable value, it saturates at the maximum representable value. And similarly, there is no underflow to 0. So these are like some of the design decisions that are different with posits compared to floating point. And the other thing is there's only one rounding mode, which is round to nearest, which ties to even. Okay, so.
Hey, Santosh, sorry, I have one more question about the posit design. Can you say a little bit more about this kind of taper precision? So I'm not super familiar with the floating point design, but if I remember correctly, there's also this exponent in like a mantissa. So at larger, scales, you have fewer floating point numbers. So is there something very different here that's happening with posits, or like how, do you mean that it's taper precision?
Let's look at normal values, right? Typically, what is a normal value? In a 32-bit floating point, like you have 8 bits of exponent, and a bit pattern which is not all zeros, which is not all ones, is a normal value, right? So what is the range of exponents that you can represent? Like you can represent 2 to the power of 54 minus bias, which is 127. It's either 2 to the power of 127 to 1 minus 127, which is 2 to the power of minus 126. Right? This is the range of exponents that you can represent. All these numbers have exactly 23 bits of fraction available for them. Okay, because you use 8 bits for the exponent, 1 bit for the sign, you're left with the remaining 23 bits. Sorry, in a 32-bit. So everything has 23 bits. In contrast, in posits, so you have this regime which can extend to the entire number, or it can be as little as just 2 bits. So you can repurpose. So you have at most 27 bits or 28 bits of precision with a 32-bit number.
I see.
For some values, you can 28 bits of precision. So it's not about spacing. Like you're representing real numbers with finite number of bits. As you go larger, the numbers will be widely spaced. But it's not about spacing. So posits also has space. The numbers are widely spaced. But like how much precision do you have to represent intermediate numbers? So with smaller values, you can represent more values densely. As you go farther away, you probably don't have like much precision bits left at all. Thanks. I think this is like the key idea of tapered precision. Okay, so let me like
what you said is true, right? So there's 2 to the 23 values for any given exponent, and then for the exponent 1 larger, there's the same number of values, but they're twice as far apart.
Yeah, sure.
In standard IEEE floating point.
That's true. Okay. Again, tapered precision is appealing. Like again, there are people like who are very conversant with IEEE. They may say, "Man, like now I'll have to do all my numerical analysis again. So it's like tedious. Like I don't want to use any new representation, but like for people who are reinventing number representations for performance or whatever reason, so this is an interesting opportunity. Okay, so one of the facts of life when you deal with number representations for floating point is you cannot represent all values exactly. So you have to do rounding. You'll have some error. What IEEE and most number systems do is they classify how much error you're going to have with each primitive operation. So you're going to have some error, but it's quantifiable. But what happens is it's the accumulation of error with a sequence of operations. That's what causes counterintuitive behavior. So like your rounding errors accumulate and then you cancel out and your entire results may be affected by rounding. That's when like these are like catastrophic errors that sometimes show up in applications. Okay, so tapered precision, one of the drawbacks of like tapered precision, like who are coming from the floating point world, is like you have two operands. Like so you're doing a multiplication. Your result may have lower precision than your operands because you multiply two numbers, you're going to get a large number. Now it may have like very little precision bits compared to your operands. So which is kind of counterintuitive for people coming from the floating point world. And saturating behavior at the maximum value and the minimum value also sometimes causes weird, like people expect 1 by minus infinity should be 0. But there's no minus infinity, so you saturate it, like you may have counterintuitive behavior. So the bottom line is Posit is an attractive representation. So is it a stand-in replacement? I let the community decide. We got excited by it for some domains that we are looking at.
Can I ask a question?
Yeah, sure.
So it seems to me, this is Mark again, the most likely place people will do a new representation is in machine learning systems for training where they want to have very small numbers, 16-bit values, 8-bit values or something. Does this representation have an advantage as the number size gets smaller vis-a-vis IEEE floating point?
So you can provide much higher dynamic range than a half or a whatever, like 8-bit floating point. Like for example, the dynamic range of a half precision floating point in IEEE standard is not good enough for neural networks. That led to the birth of bfloat 16, right? They wanted to increase the dynamic range because they were like hitting like exceptional values everywhere, like infinities. And then like one of the reasons what NVIDIA is proposing TensorFloat 32 is, again, like we want like we just don't want like very large dynamic range. We also want precision. So how do we reconcile? So can we have the dynamic range of bfloat 16 but the precision of half? And this is where what led to the 19-bit floating point. And by carefully using the parameters n and es to design a posit, like you can actually reconcile both of them and provide like even have a systematic exploration of the entire space. So I think like with smaller precisions, posits have a role to play. And what John and his collaborators have shown is like, at least for neural networks, like you can train much more efficiently compared to traditional floats. Okay, so posits are interesting. There are a lot of people who are excited about posits. I was excited about posits a couple of years too, and I wanted to see like what are the pain points for programmers. Like you are an application, like you don't have a PhD in math, so you want to use posits. What are the things that you have to be aware of? And this was what our interest was. And we wanted a debugger that can help. Like you have an application that you want to, that probably is written with float, and we wanted to help programmers debug and diagnose the cause of errors. And like specifically, like I design compiler optimization. How do I design specific posit related optimization? That was another motive. Like what should be fast math for posits, right? And before I go forward, like one of the interesting things about posits is like this use of high precision accumulators. These are called as Quires or Kulish accumulators, again from a very seminal result from the 1970s. So floating point allows like to fuse two operations, fuse, multiply, and add, right? So you do one rounding instead of doing rounding after multiplication and rounding after addition. So Posit mandates in the standard use of a high precision accumulator to reduce rounding errors, like so that you can provide associativity with respect to posit operations for certain computation. So this is another interesting thing. So you can, like, if you are in the certain range, and if you're just computing a dot product, like you can actually say it's associative, like associativity holds with posits if you use a high precision accumulator called the quire. Okay, so our task now, like hopefully I've given you enough background about posits so that you can understand like why we are proposing all the things that we are proposing. If you don't, like, let's say you're still from the floating point world, you just want to debug your floating point applications. How do I debug my floating point? So it's okay, you did not understand posits, you can still follow the rest of the talk. Okay.
So actually, can I just ask a question? This is Tom.
Yeah, sure.
So with what you just mentioned about dot product, if you have a sensitivity, then you can do it and log the length of the, with parallelism, you can do it with log the length of the vector then, right?
Quite possible. I don't know. Like I haven't thought about like dot product algorithms, so I don't know at the top of my head.
Well,
but like you can.
Yeah. Yeah. Okay.
But I think one of the important things about associativity is like it's important for vectorization and parallelism, and
right.
then you can reorganize computation so that it's both spatially efficient and has better latency. And by providing associativity for a certain domain, like you can do a lot of clever things. Like you can do prefix scan like designs and other things. I don't know the exact complexity.
Right,
I don't know the exact complexity of. Okay, so what are we proposing? So you have a posit applications. We want to detect and debug errors. So what do we want to detect? We want to detect if your posit program or any a program written in any representation has an error with respect to an oracle. An oracle could be an execution with real numbers, and the execution with floating point, execution with whatever representation you have. So we want to detect errors, deviations. So our idea is to do lockstep shadow execution. Okay, so we are going to do like 2 executions in lockstep. And how do you do this? And since my domain is compilers, and like within compilers, you can do a lot of interesting things. We are proposing a compiler instrumentation. And our goal is to detect cancellation. What is cancellation? You have an operation, all the leading higher order bits are all canceled out, like your entire result is influenced by rounding. So this is a cancellation. We are interested in detecting errors such as differing branch outcomes, or your results are different, exceptions. And these are all the kind of errors that we want to detect. So we want to use lockstep shadow execution to detect divergence of 2 executions. What are the 2 executions? The floating point execution or a posit execution versus an oracle execution. Oracle could be a real execution with reals. And just saying your program did wrong is useless from the programmer's perspective, right? So you want to help them debug and diagnose the error. So to diagnose the error, we want to provide them, like when an error occurs, we want to provide them all the instructions responsible for the error. So we want to provide them a directed acyclic graph of instructions. Okay, so which resulted in which caused the error. And these instructions could span like multiple functions, multiple libraries. So we still have to provide some useful information. And the key thing when we are designing such a debugging support is we want to run it with long-running applications, which is simulating for a couple of days or months, right? So we don't want like your program to run be applicable only for small unit tests. So the key design point that we want to do is we want to maintain additional information. And this information should not be proportional to the number of dynamic instructions. Your program runs for a long amount of time. You run it for 1 minute, you're already executing billions and billions of instructions. Your information that you maintain should not be proportional to the size of your execution. So these are the key design goals, and what I'm going to illustrate, how do we design such a shadow execution framework? And I'm going to like specifically talk about in the context of posits, but like it's a generic shadow execution framework which you can use with any type of interest. Like you are interested by bfloat16, use bfloat16 with whatever oracle you want, and it should work. So it's publicly available. Okay, so how does the user see this PositDebug framework? You have a floating point program. You just want to do shadow execution of floating point with reals. You don't have to do anything, just use our tool and you can do it. But if you want to do shadow execution of posit program, so you have a million line floating point code and you don't know you don't have POSIT code. So you don't want to like go back and rewrite every line of it. So we have a simple refactoring program in AST to AST refactor that takes a float program and converts it into POSIT. And my student is working on converting bfloat16 and various other things. Now you have a POSIT program. Now you use the client compiler, generate like LLVM IR for it. And for each POSIT operation, we are going to instrument like make additional calls to our runtime that does shadow execution. And when you create the binary, so your program executes with inline reference monitors for each floating point execution, each floating point instruction or POSIT instruction to perform shadow execution. Okay, so this is at a user's view of like how would you use it. So I'm going to illustrate like how are we going, what is the information that we need to maintain, how do we make everything work. So this is a very simple program that I'm going to have. Like again, the details of each instruction are not important. I'm just going to illustrate what happens, what information do we maintain using this program. So typically, you have a program. Where are the variables? Like where are the floating point variables or POSIT variables going to be resident? In a compiler world, there are only two places where it can be resident, right? They are either resident in registers. These are temporaries. And typically you can use LLVM compiler or any mainstream compiler. There are infinite number of temporaries. Okay, SSAIR, right? And then they are resident in memory. Okay, so they're either in registers or in memory. Now the next question is, to do shadow execution, we need to maintain additional information. Okay, so for values in registers, the metadata, the additional information that we maintain could be larger than the size of the register. So that's why we can't maintain the metadata in registers. So we maintain it on the stack frame of the exact function, or same function itself. Like if there's a function foo, you have temporaries in function foo, the metadata for all the temporaries in function of function foo would be on the stack frame of the function foo. So why do we maintain it on the stack? Like we don't want to do any additional thing, right? When the stack frame is deallocated, the metadata is also deallocated. So we are not like unnecessarily growing the metadata. And for values in memory, we are going to maintain it in shadow memory. So you can organize your shadow memory as using various data structures. One tries a good data structure to minimize memory footprints. You could use it as a hash table or whatever data structure. Like you shadow every byte of memory with shadow memory. So the next question is, what information do you maintain for each register and what information do you maintain for each operation in memory? So let's say in this program, in this snippet that I'm showing, like you have a temporary operation, you're doing a subtraction. You're subtracting T1 from T1 and T3, and like you're producing a new temporary T4. So our goal is to detect whether you deviated from an Oracle execution. So you need to maintain the Oracle value. In this case, it's going to be the MPFR, like a real value, or any Oracle execution value in general. So what do we do? Like we compare the value produced by the program and this real value. If they differ, if they significantly differ, that means there is an error. So you maintain the Oracle value. And one of the things that you have to do when you have a long running application is you cannot have an all or nothing shadow execution pass. The reason is like you have a million line code base and it runs for days, and you're only interested in one or two functions. So and these functions could be called in like various places, right, in your dynamic execution. So you should have you should have the ability to execute shadow execution selectively. Okay. So to do this, we store the POSIT value of the program in the metadata itself. So why is this important? Let's say like there is uninstrumented code, uninstrumented from the perspective of shadow execution, and then there is instrumented code. Okay. So you need to, when you get into the instrumented world, you'll be performing like a lot of updates to shadow registers or metadata on the stack or metadata in memory. But when you're in, and the uninstrumented code may interfere and like update these values. So in those cases, you should be able to detect that uninstrumented code actually updated your updated the value and your metadata is out of sync. So to do this, we maintain the POSIT value in the metadata space. So let's say the program loads a POSIT value, and it loads the POSIT value from the metadata space. If they mismatch, it means that there was some uninstrumented code that updated the memory, but since it was uninstrumented from the perspective of shadow execution, it did not update the shadow memory or the metadata. So, and then you can detect detect that uninstrumented code had updated values and reset your shadow execution so that you can avoid reporting spurious errors. So this is what, like, maintaining the posit value in the metadata space. That is what allows us to do selective shadow execution with long-running applications. And then what we need to do is we also need to, on an error, when we detect an error, we need to report what is the root cause of the error. To do that, we maintain pointers to the metadata for the operands. In this case, there are two operands, T1 and T3. We maintain pointers to them. Okay, so we have real value, the posit value, and pointers to the metadata. And this is for temporaries on the stack, or temporaries in your program. Now, when you have memory operation, like you're doing a load or a store, what information do we maintain in shadow memory? So first thing is we need the real value. And we need the posit value again to do selective instrumentation. All arithmetic operations happen on temporaries. You only store the value into memory or load the value. This is a canonicalization of your entire program, right? Into a load store instructions and arithmetic operations. So to maintain the provenance, to provide this directed acyclic graph of instructions, we also maintain a pointer to the metadata of the previous write. This, which is a pointer to the metadata on a stack frame, right? So now you guys may be thinking about it. Man, you're telling me you're maintaining pointers to stack frames in memory. What if the stack frame is deallocated? Now you have a dangling pointer, right? So yes, if the stack frame is deallocated, these pointers could be dangling. Yeah, these are pointers to the metadata on the stack, right? So we need to enforce temporal safety for them. And to do this, long back, I proposed a technique called lock and key to enforce temporal safety of C programs. Again, inspired by one of former Wisconsin faculty members, Charles Fisher. He had a cool idea long back with Harish Patil in 1994. And in my PhD thesis, I was inspired by it. I tuned it a bit. And now it's like in the security community, people are all excited by the idea, and people are using it. Let me illustrate the idea carefully with an analogy. So let's say you are the landlord. You have an apartment to rent. Okay, you are the landlord. You have an apartment to rent. I, the tenant, wants to sign your lease. What do? So you assign a new lock to the apartment, make it operable with a key, and give the key to the tenant. And as long as the lease is valid, the tenant can enter the apartment with a key. Okay, and this tenant may be malicious. He or she copies multiple keys and gives it to multiple people. When the lease expires, what do? You don't go in search of all the copies of the key, right? Like you just change the lock, and so the tenant with a stale key will not be able to enter the apartment. So the lock and key approach that I proposed is actually inspired by the same analogy. The landlord is the runtime. The tenant is the pointer. Okay, so when a stack frame is allocated, you allocate a location in memory called the lock, write a unique identifier to it, which is the key, and give this key and the lock to the pointer, which is the tenant. As long as the stack frame is valid, the pointer, the key associated with the pointer and the key at the lock would match. When the stack frame is deallocated, they won't match. So when the stack frame is deallocated, the runtime updates the value invalidates the key at the lock. Okay, so only the runtime can change the lock. The pointers can read it. So this is the invariant. So you can do this with 3 operations, like a load and a check. So this is why it's appealing to do temporal safety. So you have to maintain lock and key metadata with every pointer to the stack that you maintain in the metadata space. Okay, so this is the high-level design. So what information do we maintain with each register, and what information do we maintain for each memory location? Now I'm going to run through with an example so that like everything becomes crystal clear, right? So your program variables are resident in registers and in memory, and you have shadow memory. I've initialized all the state. So in the shadow memory, I'm going to show you just the real value, the posit value, and the previous writer. I'm going to elide lock and key for simplicity for now. Okay, so what is the first instruction that is happening in this program? You're dereferencing PTR1. Okay. So what do? So what does the program do? When you dereference, you go to memory at PTR1, load the posit value. That's what happened. So you loaded the posit value into a temporary, which is a register. And what happens in the shadow execution? You go to shadow memory. Since you're writing to a temporary, you have to store the temporary metadata in the stack frame. So it will be the stack frame of the function foo. Okay. And then you go to shadow memory associated with PTR1, load the posit value, load the real value, load the posit value. And now you look at the previous writer. If the previous writer's pointer is valid, temporally valid, then you copy the operands of the previous writer's pointers. In this case, let's assume like all the pointers are invalid. Like we don't know what P28 right now is, right? Let's say it's invalid, then you initialize the operands to be null. So you lost provenance at this point. So the key thing is we still provide you a DAG of instructions, but the instructions from the DAG belong to the calling, will be instructions in the calling context or the backtrace of the execution. So if it is in a function that was previously executing but has since completed, you won't be able to get the DAG. So this is a trade-off that we have to do to maintain metadata to be a constant size while still providing the ability to give it generate a DAG. So this is the metadata for A now. So now next you do the same thing for B, you do the same thing for C. Now you make a function call. So it's a new stack frame that is being allocated. This is the root count stack frame. In this case, you are doing like a new temporary, T1. You're computing a new temporary and you're multiplying B and B. What does the program do? It computes the value of T1. Now you're creating a new temporary. You create the metadata for it in the root count stack frame. And what will the metadata have? It will do the Oracle execution with B's metadata, which is what is B? B is the operand, right? It uses the B's metadata to compute the Oracle value. And then it uses the program's value to store the program's value, which is the posit value. And then it has two operand pointers, which is both are in this case happen to be B. The same thing happens for T2, same thing you do it for T3. And when you execute T4, you observe the Oracle value is saying some value and the posit value is saying something else. So this means that now you're encountering a situation where the results are totally different. Results of the Oracle execution and results of the program execution are totally different. All bits are wrong, probably due to rounding errors. Now you want to diagnose what is the cause of this rounding error, right? What is this cause of like cancellation error? So this is where you use the metadata and generate the DAG. So T4 is a subtraction operation, and it has two operands from the metadata, T1MD and T3MD, so which are like T1 and T3, which both happen to be multiplied, and then you generate a DAG like this. And in the case of POSIT, what you observe is, so everything, I'm representing everything as 64-bit POSIT, so the multiplication operation had an error of 43 bits. That means the only 19 bits, or like 21 bits were exact. 64 minus 43, 21 bits were exact. Like you lost all others due to rounding because you had some precision, you lost precision with multiplication. And then this got amplified with subtraction. When you subtracted, all the upper order bits got canceled away, all the rounding errors, all the bits that were influenced by rounding became prominent. And this shows that you have a program which is experiencing catastrophic cancellation with the subtraction. And this was actually the result of precision loss with multiplication. And this is pretty useful. Like we found it useful in our endeavor to detect like why the numerical errors were happening. Okay, so when the program completes, you return the root count stack frame is deallocated, and you come back to the foo function and you have T5 now. At this point in time in T5, you can still detect that the value produced by the Oracle execution and the program execution are different. But you won't be able to generate the DAG now because T1 and T3 both are dangling pointers. They point to deallocated memory locations. And our temporal metadata would say you can't access them. Okay, so at this phase, we detected the error. At this point in time, we detected the error, but we won't be able to give you a DAG. So what is the programmer expected to do? The programmer is expected to put a breakpoint just before root count completes to get the actual DAG for these instructions. So this is one of the trade-offs that we did to make it run with long-running applications. We don't want metadata to grow unbounded, grow on an unbounded fashion, but we still want to give the programmer the ability to debug numerical errors. So this is the generic shadow execution framework that that we built and which was presented at PLDI. So you can run like any favorite number representation of your choice. It works, it scales well. And using this, we tested out numerous applications. And one of our goals was to test fast math optimizations and math libraries. And we were building math libraries for posits and floating point, and we were testing it out. And it detected numerous errors, and we have contributed to FPBench, which is a open source collection of all numerical errors that various groups are collaborating and maintaining. And what we found was this interactive debugging with GDB was amazingly useful. And how much is the overhead? Like nothing is free in life, right? So if you do shadow execution with real numbers, approximated with 256 bits of precision, compared to an Oracle execution with spec and polybench, we are about 12 times slower. So this is assuming like you're instrumenting every function, every floating point variables. In reality, like what we really do is just instrument the handful of functions where we detected an error, and the overheads are like roughly in 10 to 20% ranges. Okay, so with this shadow execution framework, we tested numerous applications, and then what we discovered to our surprise was most of the time the error arises because your math library disagrees with whatever your program is producing. So you have a shadow execution done with real numbers. It produces a value from your math library, and then you call your program's libm's math library. It's producing totally drastically different results. So it's not producing the correctly rounded results. And we started investigating why. And let me tell you, like, what is a correctly rounded math library? Okay, so let's say this is your real number line. These are all the real values, infinitely many real values numbers, right? That are present. And given a number representation, there are finitely many of them that you can actually represent. So for simplicity, I'm just spacing them. I'm spacing them equally here, but like in reality, they'll be like differentially spaced. Some numbers will be closer, some numbers will be further apart, right? So now, what is a math library? You have an elementary function such as log x to base 10. Okay, you call it on an input 1.8, and you evaluate with real numbers. It produces a value. Okay, it's generally another real value, so it probably is not representable in the representation that you're looking at. So what do? You compute it with real numbers, and then there's a rounding mode. In the case of posits, it's round to nearest with ties to even, and this is what the result that you need to produce. So this is the correctly rounded value. So you compute with real numbers, compute the elementary function with reals, and round the result. Okay, and this is the correctly rounded result. If your math library produces the correctly rounded result for all inputs, it's a correctly rounded math library. When what we found is mainstream math libraries, I use libm, it produces wrong results. Why? What are the ramifications? Like, yeah, there's approximation everywhere, right? Like, who cares, right? So, well, if you want reproducible results, you care about like at least it's math library, right? Not approximate library. So you at least want it to produce like some modicum of truth, right? So there should be some truth in whatever the value you are reporting. So if you care about reproducibility, you may want your math libraries to produce the correctly rounded result. You want portability, you may want to produce the correctly rounded result. And people who care about standards, IEEE 754 standard, like for floating point, recommends that the math libraries produce the correctly rounded result. It does not mandate, it recommends. Okay, so let me tell you, like, give you a quick tutorial on how people generate approximations for math libraries. Okay, so this is a real function that you want to, this is the elementary function that you want to approximate, log x to base 10, right? So what do you typically do? You generate a polynomial. You generate a polynomial that approximates the real value of the elementary function. And what is the general approach that you use? You use Chebyshev approximation algorithms or Remé's algorithm to do that. These algorithms are typically called minimax algorithms. What is a minimax algorithm? You minimize the maximum error for all inputs. So this is a key algorithm. Almost every library uses it. Okay. So what is the end result of it? There is going to be some error because it's an approximation, right? There is some error. This is the error with respect to the real result and the polynomial approximation with reals. And then you want your math library to be fast. So implement the polynomial approximation with some higher precision, generally with doubles. Double is the highest precision supported on your hardware, right? Implement this polynomial approximation with double. So double is a finite precision. There's going to be some rounding error with respect to the polynomial approximation with reals and the real value that you generated. Okay, and then finally you have the approximated result and you round according to the rounding rule of the target representation that you are going to get, and you're going to get the wrong result. Okay, so this is what we observed, and one thing that motivated our approach is math libraries need not approximate the exact real value. So if you're designing a math library, producing the exact real value of an elementary function is not the goal. What should be your goal? Your goal should, for a given input, you should produce the correctly rounded value. Okay? So our approach deviates from the standard convention where they generate polynomial approximations using the minimax approach. So in our strategy, our key insight is it's not necessary to approximate the real value of an elementary function. Our goal should be to approximate the correctly rounded result. And given a correctly rounded result, there is an interval of values. If you produce any value in this interval, as long as you produce any value in this interval, it will round to the correctly rounded result. This is the margin of error for whatever approximation that we are going to design. Okay? So the key insight is look at the correctly rounded result for an input, generate an interval, and design a polynomial that produces a value within this interval. So our approach is, how do you identify this interval? You use an oracle to identify the correctly rounded result for an input and the interval where it rounds to the correctly rounded result. And then we are going to generate a polynomial that accounts for all numerical errors, and so that the final evaluation result of the polynomial lies within this interval, so that it rounds to the correctly rounded result. And we frame this as a linear programming problem. So let me give you a quick tutorial, like since I'm running out of time, like quick overview of like how do we do this. The x-axis here are all the input points in your representation. Like this is Posit 16, these are the values that you're representing. And y-axis is the result of the elementary function. Right. And for simplicity, I'm just showing a straight line, like very zoomed in view of the elementary function, which happens to be a straight line in this case. Okay, this is the oracle value. Since you cannot represent the oracle value exactly in the representation that you're looking at, you're going to identify the correctly rounded result for each of these input points. Okay, this is what you should be focusing on. Okay, now we forget the oracle completely. So we know the correctly rounded result for all inputs. We identify the interval for each of these inputs. And now this is what we have to focus on. We need to generate either a single polynomial or a piecewise polynomial that satisfies all these points. Okay, how do you do this? Like this polynomial has to be satisfied when evaluated on this point, has to satisfy these inequalities. We can frame this as a system of linear inequalities. Ask an LP solver to produce me a polynomial of degree d that satisfies all these inequalities. We use an arbitrary precision LP solver to identify the coefficients for them. And this is our approach. Very simple. Don't look at the real value of the elementary function. Look at the correctly rounded result and identify an interval for the correctly rounded result, so that like you round to the exact correctly rounded result. And then using this interval, generate a polynomial or a series of piecewise polynomials to produce the correctly rounded result for all inputs. We use this approach and built the correctly rounded math library for Posit 60, bfloat 60, and even floating point. And our implementation actually uses doubles to implement everything. So it's very fast. And it produces correctly rounded result for all inputs. And I want to conclude with this parting thought our bfloat16 library is 2.3 times faster than Liban, and it produces the correctly rounded result for all inputs. If you're interested, there is an archive paper that I just put out, which has a lot more details about how do we do range reduction, how do we do output compensation. The devil is in the details, right? I'm giving you a high-level overview of the ideas here. Okay, so I'm running out of time, so let me conclude. So this is an exciting time to be looking at number representations. There is, like, if you are a static analysis person, you are a hardware designer who wants to design debugging tools, add debugging support, this is an exciting time to be doing static analysis, dynamic analysis, accelerator support for number representations. And what I presented to you was two pieces of work, like a generic shadow execution framework to detect and debug numerical errors, and a novel approach to generate correctly rounded math libraries. And what got me excited about all of this stuff was there is an opportunity to influence the standards of new representations. Okay, so I just advertise the work that my students put day and nights to get it done. So these are my students in my group. Some of them have graduated and are doing cool things elsewhere, but others are doing even more cooler stuff. My group works, I was advised by a computer architect whose heart was in programming languages, who's enamored by verification, who now works on verification. So I have a checkered past. So, but I also dabble in hardware design. I also dabble in compiler design. I also do some formal verification. So there's a lot of cool projects from my group. And lastly, I want to thank all the people, all the agencies that have generously supported my research. With this, I'll conclude my talk, and thank you for your attention and the feedback that I had till now.
So I had a question. I mean, Posits is what enables us to be one important driver. What is the opinion on Posits from like numerical analysts like Jim Demo, who's a student of Val Khan, or Jack Dungera?
If you're really curious, John Gustafson and William Kahn had a YouTube shout out. It was in Arith 2015. It was interesting, like it's humorous. You can go ahead and look at it. This is like, I think it's difficult. Like I think IEEE 754 was an exercise in compromise, right? So the multiple vendors, how do you like reconcile and design something that satisfies everyone? And someone is going to be happy, they're unhappy. Someone is going to be happy, someone is going to be unhappy when you reconcile and do various things, right? So I don't want to get into this debate of Posit is best, Posit is not good. There are definitely, so one of the challenging parts with Posits is doing numerical analysis. Like most of the people, like most of the work in the floating point domain has been like quantifying the error of numerical algorithms, and that takes work and it's challenging. And Posit is so new that there hasn't been enough work. And my group is looking at like quantifying numerical error for a lot of numerical algorithms going on. So I don't know like what the specific opinions, like I've spoken to James Demel and Jack a couple of times, but like I don't know their opinions about Posits. But I do speak to a lot of hardware vendors at various companies. They are excited about Posits. They actually explored, like some of them have actually explored incorporating as part of their new ASICs. And there are at least a couple of them who are interested in using them. So I would say it depends on who you're talking to. Like,
yeah.
This is Tom. I have a couple of questions. How much of a problem in your debugger is the fact that you lose the DAG after a function returns?
Well, it depends on what do you mean by a problem. Like this is a design point that we stuck with, in the sense like our goal was like we wanted to take a long running application like some of the large simulations at national labs and still be able to debug them. There are situations where like you call a short-lived function it does something and returns back, and then you make some computation on it. So then we lose information. In those cases, like what you typically do is you observe an error. Oh, I'm not able to produce because the pointer was to a recently completed function. So you know what the function is. So you run the debugger again, like set the breakpoint there, and you'll get the data. This is the methodology that we adopted in debugging our when we experience a numerical error in our experience.
Yeah, I was thinking that it's not, I mean, it seems like the problem might be that you might be able to scavenge the metadata from the stack frame as you return. It would be a little bit like, you know, semi-space garbage collection or something like that, that you would just sort of move that material off to some other space that is, yes, it's continually growing, but you know, it can get written out to disk or.
Yeah. So that's a fantastic design idea in the sense like rather than deallocating it, maybe like maintain it in a separate space and then you use it. You bound the space. It's like a best effort hash table, right? Like we haven't explored a couple of things. Like most of them are engineering issues rather than like algorithmic issues in a sense. One of the things is we didn't want to get into this business of managing the metadata for the stack because it becomes pretty expensive, especially with the long-running applications. We didn't want like to have additional layers of indirection for the metadata of the stack. So this was a pragmatic design point that we set out with. But that said, like whatever you are suggesting, having a nursery for a stack space and then using it to do some best effort reclamation of metadata, that's actually a good design point. Like we haven't evaluated it yet.
Maybe for the next student. I thought your approach to getting the right answer from library code was really, really cool. But I do have a couple of questions about rounding error in that process. So one is that you create the LP problem and then pass it to an LP solver, but most LP solvers kind of ignore rounding errors themselves. So
yeah, so that's why
right.
That's a fantastic question. So this is why I said you use an arbitrary precision SPLP solver. So there is a nice solver called Soplex, which uses rational approximations, which is not arbitrary precision, but precise enough for our purpose. So what will happen when we use an arbitrary precision LP solver like Soplex, it will give me coefficients. We validate it. We test whether it produces the correct output when we correctly rounded output. If it does not, what we do is we refine the intervals further so that whenever we evaluate with like finite precision such as double, it produces the correct precision.
I see. So you could start, it's almost like a bridge builder that you can say, well, my tolerance needs to be tighter because. Yeah,
precisely. And this is like rather than relying on the programmer to do this, like the tool, this is like counterexamples for interval refinement in some sense. Like if you come from the verification world, right? It's Sedge is done for interval refinement.
Right, but then you get the coefficients and then you evaluate those in double precision. So then there's yet another round where you might get accumulated error.
So effectively, how do we generate these intervals? We use an oracle to generate the interval. And typically no one, like if you look at any math library, they don't take like approximate for all inputs, right? They do range reduction. So it's approximating a polynomial over a small input domain is much easier than over the entire. So there is a range reduction function. And then for the range reduction function, there is an output compensation function. Like you produce an output on the reduced input, and then you have to compensate it for the final output. And this output compensation is done in double. So what do we need to actually do is when you generate the interval, you need to compute the inverse of the output compensation function. So, and take the original interval that you have, use the inverse to compute the reduced interval. And then when you generate the reduced interval, you need to look for what is the implication of evaluating the polynomial with double and further reduce the interval. And this is what you give to the LP solver.
Right. Okay.
So this is a preconditioning step that I elided in the talk just for simplicity.
Yeah. Okay. Thanks.
Thank you.
So I think we are quite a chunk over time, so probably we should stop here and we can thank Santosh again for his talk. Thank you.
Again, thanks
Thank
again
you.
for inviting.
Yeah, thanks. That was terrific.
Thanks.
Thanks a lot, Santosh.
Thanks, Justin.
Bye.
Bye.
Bye.